I sent an email out earlier today with some announcements. I just wanted to briefly review those. I reorganized the Moodle page a little bit. I separated out the different types of downloads. I've got the Lecture 5 slides online. I added Quiz 6 solutions. Quiz 6 was the last week's quiz. I also added this, somebody asked about a Verilog or System Verilog simulation tutorial, like the ones that I did in class, last couple classes as a live demo. So I added some slides that show you how to get started with that if you're interested in practicing Verilog. So I've got a script that you can run. This is in Linux. You log into any of the lab machines, departmental lab machines. There's a script that you can run to set up the simulator and the synthesizer. Then it brings you through a little example here. There's a full adder module that you can write. Then this chains together 10 full adders to create a 10-bit adder. And then it shows you an alternative way to generate the same code with this generate loop, which I didn't cover in class, but it's a nice little example. It's basically just shorthand for instantiating a bunch of different components. And then there's a add parameters to it. This is a register design, and then finally it creates this adder data path where there's 2 input registers, an adder, and 2 output registers. And then finally I give you a test bench, which is going to be hard to read in the back, but you can take this code and you can try it out. This is a test bench for that adder data path. And then to simulate that, you can start up ModelSim with the vsim command, which gives you a little splash screen initially, which you can turn off. And then it goes through what the various windows are in ModelSim, and then shows you how to get started to simulate the test bench. So if you're interested in practicing, that's a nice resource to have, I think. Let's see, I found some two example quizzes and an example exam from past versions of this class that are on the topic of Verilog. And so those are the types of questions I'll be asking on this upcoming exam. So you might want to check those out. I've got 3 examples with the solutions. And finally, we've got quiz 7, which should have just activated just now. And make sure you take that by this Friday. So this is also on this is our second quiz on chapter 5. Hey, any questions? Okay, so last time we finished up chapter 5, and we have our exam on chapter 5 on Wednesday. I wanted to just very quickly run through the chapter 5 material just to check if anyone has any questions. I'll do another brief review on Monday of the chapter 5 material, and then and other than that, we'll be on chapter 4, Verilog. Yeah, sorry. Is that what you're going to ask? Yeah, sorry, I misspoke. Chapter 4. The exam is on chapter 4, the Verilog stuff. Yeah. Sorry, chapter 4. Okay. Oops, sorry. Chapter 4. Okay. Okay, so chapter 4 was on System Verilog. Sometimes I just call it Verilog. System Verilog designs are composed of modules. You can define a module. Inside a module, you can create other modules. You can also have behavioral code. Behavioral code is generally Boolean logic and is implemented in either an assign or an always statement. Here's an example of an assign statement. Assign statements are for simple Boolean logic. got a list of the various operators and their precedence. I mentioned last time that this is not actually a comprehensive list. There's a few others in here. These are the main ones, the most common operators. Whenever you have a number in Verilog, a constant number, you should always specify the width in bits first, and then an apostrophe, and then the base, and then the actual number. I pointed out that in some of the book examples, they don't do that. They don't show the widths. That's kind of bad form. It's best to specify the width of any kind of constant that you have listed. We covered bit twiddling. If anyone has any questions, by the way, stop me. I just want to run through and make sure everyone's on the same page here. So bit twiddling or bit manipulations, you can combine, you can concatenate signals together into one signal with these curly braces. There's also this strange one here where you can take a bit, or probably multiple bits, although I think every time I've ever done this has been with one bit, but you can replicate it with this replication operator, right? So in this case, this takes bit 0 of B and puts 3 copies of it there in this Y, in this signal here that gets assigned to Y. Okay, is everyone clear on this? Okay, we talked about putting delays in. You can insert a delay into an assign. You can also put delays into always blocks as well, which we covered under the Testbench section. Sequential logic is, whenever you use sequential logic, meaning any logic with memory, any memory, has to be described with an always block or an always statement. In Verilog, you just have just a plain always. In System Verilog, they have different versions of the always statement that is designed as a way to avoid bugs in your code. So if you have always underscore FF, that tells the synthesizer or the simulator that you are designing an always block that's designed to implement a flip-flop style edge-triggered memory. So it's good to use that. So always underscore flip-flop. You still have to specify the sensitivity list, which is usually pause edge clock, and sometimes pause edge clock, comma pause edge reset if you want an asynchronous reset. Is everyone clear on that? Okay. Okay. Also mentioned, you should use blocking assignment statements in a sequential always. You don't have to, though. You should. It's a convention. But sometimes you might not want to. Sometimes you might want to put blocking. Sorry, this is non-blocking. I say that right? Non-blocking is the little arrow looking thing. Non-blocking. Blocking is when you just have a regular equal sign for the assignment. So there's actually, I've got a question on the quiz where it asks you to predict the behavior of an always with a mixture of non-blocking and blocking assignment. Let's see here. Latches, not a big deal. Should avoid the use of latches. We covered the case statement syntax. This is really just a syntax thing you need to remember, how to build a case statement. One thing you should watch out for here is if you want to put multiple, there's no break in the case statement as there is in Java and C. But if you want to put multiple statements for each case, you need a begin and end. I point that out because I often forget to do that myself. Blocking and non-blocking assignment is kind of subtle. It's a subtle distinction. But the way to remember it is, in a non-blocking assignment, the assignment takes effect after all of the actions associated with a particular event have been evaluated. Okay, so in the book uses the example of having one always block. So there's one always block here, there's one always block here. This always block has non-blocking assignments. it assigns D to N1 and then N1 to Q. So when this always statement activates, the second line that uses N1 as an input is going to see the old N1, not the new N1, as set by the previous line. So in other words, when you use non-blocking assignment, the assignments don't take effect until, in this case, until the always statements is done executing, until it's been fully evaluated. You guys with me? Right? Now, it's a little bit more complicated than that in reality, because it's not necessarily just restricted to one always statement. If you have, if you put blocking assignment in, then in this case, D is assigned to N1, N1's assigned to Q, but with blocking, the N1 is going to be updated right after that line of code, so the Q is going to see the new N1, which means in this case that this code reduces down to just a single flip-flop, right? These two lines are kind of redundant. You guys with me? But as I was saying earlier, this behavior extends beyond a single always. It actually has to do with the event that triggers the always from executing. So in other words, what I'm trying to say is if I had let's say I had two always blocks, and I executed this first line in one always block and the second line in the other. In other words, imagine I had two of these always blocks, and in one of them I just had the first line of code, and the other one I just had the second line of code. It would still produce the same behavior. It would still reduce, they would both basically collapse into one flip-flop. Why? Because the N1 would be set on the rising edge of the clock, and all always statements that are sensitive to that rising edge, that are sensitive to the rising edge of the clock, would see that change right away. Make sense? It's hard to explain, and I always run into trouble with this, which is why it's best to follow the convention. Make sense? Yes?
So in the event of a blocking statement, does this imply it's going to wait the number of cycles necessary for that state to propagate?
No, well, it would, in this case, this statement would just, it would basically update N1 and Q at the same time, right? And they would both be D. They would both get D, right? So it all happens like, instantly, right? Yeah, so assignments, blocking means assignment statements take effect right away, is one way to remember it. Whereas non-blocking, it's deferred. Assignments are deferred until after everything settles down, after the event that triggered the actions. Okay, does that make sense? I don't like covering this because it's hard to explain, but it is a very important, it's something that comes up quite a bit when you're writing in Verilog. So it's important as a Verilog programmer to understand this. Okay, and then finite state machines are pretty natural to express in Verilog if you understand how they're implemented in hardware. So they have a clocked, I want to say clock process as VHDL, clocked always statement, where you handle reset and transitioning and setting the state to the next state on the clock edge. So this is your flip-flops. These are your state registers. Then you have a next state logic, which is combinational, and an output logic that's combinational. The next state logic just sets the next state, and the output logic sets the outputs. Okay? And we talked about parameters. Parameters are useful when you want to be able to customize a module when you instantiate it, as opposed to when you're designing it. So in this case, I want to be able to create a mux that does mux stuff, but I want to be able to determine the width of the input ports and the output port for each mux that I instantiate. So in this case, I have this width parameter that allows me to set this is always a 2-to-1 mux, but I can control how big the inputs and output are in terms of their bit width. Everyone with me? So having the width, being able to control the width is a common thing that you're going to do with Verilog. And then the last topic was test benches. The idea with this is that you have a module that doesn't take any inputs or outputs. It's kind of a self-contained module because it creates inputs, it sets inputs, it sends those inputs into the design under test, the design that you're testing, and then usually it also evaluates the outputs of the design under test and prints an error if there's a mismatch between the actual output and the expected output. So that sometimes those are called self-checking test benches. The problem is that there's no one way to do a test bench. You have to customize your test bench to the design that you're testing. So the examples that the book gives are kind of specific to these examples. And so this is something that's kind of difficult. There's not really a typical methodology for this. You're going to want to write. You always want to write a test bench to test your modules because otherwise, testing them is really difficult. You have to simulate them and sort of manually force signals by hand. Sometimes you can write a script to do it, but it's best to write a test bench. Test benches are not synthesizable. They're only for simulation. One of the big improvements from Verilog to System Verilog is that System Verilog introduced a bunch of new non-synthesizable features that can be used for testing. That's the main difference. As far as the synthesizable aspect of System Verilog, it's virtually identical to Verilog. Everyone with me? Also, they have whole languages devoted to verification. There's verification languages that are designed to make this easier to build test benches. But in just raw Verilog, you have to do it yourself if you don't have a product or some kind of a software that does it for you. Everyone with me? Okay. And the one thing I didn't get much time to talk about last time was this test vector file. In the example they give here, one of the problems is that you have to set all of the inputs and the expected outputs inside the Verilog. And it would be better if you could decouple the Verilog code from the actual test cases that you want to test. That way, if you want to add test cases, you just add them to a file. You don't have to go in and worry about introducing a bug in your Verilog or worry about having to type all the extra text to implement the if statements and the prints and all that kind of stuff. You guys with me? So that's what these test vectors are. So you can design a test bench that runs through a test vector file and just does all the tests in the test vector kind of mindlessly. And if you do that, then the problem is how do you synchronize things? How do you make sure that the inputs are sent into your design under test, and then the outputs are evaluated, at some after having advanced the time. So the book authors have proposed this approach where you have a clock and the inputs are assigned on the rising edge of the clock and then the outputs are evaluated on the falling edge of the clock. That is, I think, a nice way to do it, at least for a combinational design under test. And so in this case, you can write this test vector file that has the inputs and the output. You can write your test vectors in binary or hex. Depending on which one you choose, you use a different function to read the data in. And this one is in binary, so that's just the inputs, and then they use an underscore to separate the inputs from the output. The underscore is actually just ignored. And then to read that in, it's just one line of code. $read mem B stands for binary. If it were in hex, you'd use H there. And then you just give the file name, and then comma, and a a two-dimensional array that you use to read in the test vectors. The array is declared kind of funny. I mentioned this last time. It's a logic type, but because it's two dimensions, you have to have two sizes. You have to have a depth, and you have to have a width. The depth is the maximum number of test vectors, which in this case is 10,001. And the width is the size of each test vector, which is the number of input bits and plus the number of expected output bits, right? So this is 4 because there's A, B, C are the inputs, Y is the output. So there's 4 is the width, and 10,000, which is just an arbitrary number they chose, is the depth. I mentioned a pitfall here is you have to keep in mind that in Verilog, when you have a multi-dimensional array, a two-dimensional array, the width comes first, and the depth comes second, which is the opposite of how Java and C declare two-dimensional arrays. But the reason the way I remember that is because if you normally declare a multi-bit signal, you would put the width first, right? It's like here, right? Vector num is 32 bits. So the normal place for the width is at the beginning, and then additional dimensions are listed after. Does that make sense? Okay, all right. And then from that point, I think it's fairly self-explanatory. One thing that you might think, though, by looking at this is, wait a second, why not just use a for loop to do this? I mean, that's really what you're doing, right? You're saying for each test vector, test it, right? It seems like a natural use case for a for loop. Why not just use a for loop in here? Well, they don't use a for loop. They actually, it's kind of like a for loop, but the way they do it is instead of iterating with a for loop, they use the clock to increment a counter called vector num, which kind of acts like the I variable in the for loop. And then they use that to index the test vector. And then, once they index the test vector, which they do here, so vector num indexes the test vector, they assign it to these local signals on the positive edge of the clock, and on the negative edge of the clock, they read it, right? So they have this counter going, so everything works kind of together to create what is essentially a for loop. Why don't they use a for loop? That's a good question. I don't know. Generally speaking, no one uses, it's very rare to see a for loop in Verilog. I don't know I've never tried to do a test bench with a for loop. You'll notice, by the way, just to clarify something, if you're looking at that, if you go and look at that little tutorial that I published, that's called, I close it? I guess I closed it, or it was open in the browser. But there was in my tutorial, I had a for loop, but it was a special kind of for loop. It was a generate for loop that generates instances of modules. But you can do a regular for loop as well in Verilog. Okay, any questions about this? This is the last topic. Okay, great. So we're going to move on to chapter 5.
So I reckon there's going to be an email that's coming from that that's going to talk about what problems and
Oh yeah, I had that too. I'm sorry, I forgot to mention that. I also provided that here as well. If you look at the oh, it was in the email, sorry. Yeah, sorry. Yeah, it's not on the main page here. Yeah, if you look at the email, which is also shown in the announcements section here. Practice questions are 4.1 to 4.26, 4.28 to 4.50. 4.50 I like is one of those questions that asks you to look for a bug or a problem in code. I like those. I think those are kind of neat. There's a bunch of them there. The rest of the questions are mostly comprised of just write a short snippet of Verilog code to do something, implement a state machine or an encoder or something like that. So that's, and if you look at my example questions that I've used in the past, so if we back up and look at the exam that I used last semester, I say there's a question, assume the following Verilog module, and then how many total bits comprise the inputs? So, you know, A and B, 2 bits. How many total bits comprise the output? C is 1 bit. Fill in the missing values for the test vectors. This is kind of neat. So if I was testing this, if this was a module that this was my design under test, and I wanted to build test vectors, what would the test vectors look like? Well, in this case, I only have 2 inputs to this module, 2 bits of input, so I can do an exhaustive test. I could test every possible permutation of the inputs. Normally, you can't do that because there's too many. But in this case, I built this table, and it looks like that's what it's doing. There's a 0, 0, and then something and 1, and something and 0, and 1 and something. So this is the A and B should be 0, 0, 0, 1, 1, 0, 1, 1, and then there's an expected C that you would calculate just by evaluating that Boolean logic, right? So for instance, if I put 0, 0 in, that would be not 0 is 1, and 0 would evaluate to 0. So the expected C should be 0 there. Fill in the missing values for the test vector for testing module BBB. The BBB was another module, but this was structural Verilog, and in this case, I just instanced AAA. So BBB was a wrapper that goes around AAA. But I rearranged the inputs here. So inside BBB, C was connected to the A input on AAA. So the challenge here is to just essentially do what you did above, but consider the fact that the inputs have been remapped, the signals have been remapped. C is A is B, and B is C, right? So describe any problems with the code below. You know, double drive B. I got 2 always statements. They both drive B. I think that's it. Oh yeah, one other thing. This is always at star, meaning it's combinational. So I didn't use, normally in this class I would use always underscore com for this, because we're using system Verilog. In regular Verilog, if you say always at star, that's equivalent to just saying always underscore com. But whenever you have combinational logic, in order to avoid latches, you have to make sure that you assign the outputs on any path through the always statement. And neither one of these do that. Because if in this always, I don't assign B if A doesn't equal 1, right? So what's the synthesizer to do with that? It's going to generate hardware to implement an if statement. If the if statement isn't true, then what's the hardware going to, it's got to generate a voltage that does something, right? B has to be assigned to something. Every time the always activates, which in this case the sensitivity list is star, meaning the always will activate when any of the inputs change state. You guys with me? Make sense? So basically these ifs should both have elses, or they should have a default assignment for B. Yes?
If the second always is if A not equal to B to 1, is that valid?
Yeah, well, this one, this is, so I think what you're saying is these if statements are complementary of one another, right? This one's checking to see if A is 1, this one's checking to see if A is 0. Yeah, I mean, but that was intended to trick you, because if you put both of those in one always statement, it would be fine, right? But the problem is that you have complementary conditions, but they're in 2 different always, right? You don't want to put them in 2 different always statements. That's the problem. Yeah, so. Describe the process by which a user-entered HDL design is converted to a form that may be loaded onto an FPGA. We haven't gotten to that point in this semester yet, so don't worry about that question. Same thing with the next one. And then fill in the table for the module below. This one had another always at pause edge clock. This one is implementing a delay register. So you've got A and you've got B. A is the input and B is the output. But B is a delayed form of A, and it's going to be delayed by 3 cycles. It's going to take a cycle to move A into B delay 1, another cycle to go from B delay 1 to B delay 2, and a third cycle to go from B delay 2 to B. So B will lag A. If you look at A and B, B is what A was 3 cycles ago. It's kind of like looking into the past. So that's the way you solve that one. So here's A. B delay would be essentially just A, except moved down by 1 row in this table. B delay 2 would be moved B delay down by 1 row, and B would be moved down by a 3rd row. Everyone with me? And then there's an initial statement to describe what the initial values of those are. Any questions about that? Write a Verilog module that takes as input an 8-bit value and produces an 8-bit value where the upper and lower 4 bits of the value are swapped. So you're taking the 2 nibbles and swapping them. So you just use the curly brace bit manipulation for that. Write a Verilog module called find cycles having the following requirements. Clock and go. Outputs are cycle 7, cycle 11. And so that gives you a timing diagram here. This timing diagram was generated from running ModelSim on my solution. Go gets asserted, and then notice that cycle 7, 1, 2, 3, 4, 5, 6, 7. 7 cycles later, cycle 7 is pulsed. And 11 cycles later after go, cycle 11 is pulsed. The way to implement this would be, it's basically a state machine, except an easy way to do it would be to have a counter that just runs. It can be a 4-bit counter, for instance, that counts from 0 to 15 and goes back to 0 whenever you assert go. And then you just have an output logic that says when the counter is 7, cycle 7 is 1, and when the counter is 11, cycle 11 is 1. You guys see that? So it's a state, or you could implement this as a state machine with 12 states, right? You'd have an idle state, and then the state machine would kind of be linear. It would just go from one state to the next sequentially. Any questions about that? Make sense? You guys with me? So just to show you. So what I mean is that you would have an idle state, and then you'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So going from idle to this first state is when go would be 1, but then you would have just unconditional transitions. Like that, and then you could go back to idle after you're done, or I guess, what if you asserted go? What if the user asserted go on cycle 11? So in that case, you could actually potentially allow it to go directly from this 11th cycle back to the first cycle if I wanted to start counting again, if you wanted to allow that. I didn't actually specify in the description whether that would be allowed or not. But this is 1, 2, 3, 4, 5, 6, 7. So in this one, cycle 7 would be 1, and then down here, cycle 11 would be 1. And then obviously they would be 0 every other case. Make sense? Everyone pretty comfortable with that? So next state logic. So you could create an enumerated type with all of these states, that's a lot of work though. I think it would be easier just to do it with a counter. So for that, you would just say always underscore ff at pause edge clock count equals count plus 1. So there would just be one statement, 2 lines of code that would, well, it would be more than that because we don't want the counter to go until go is asserted. So we'd have to keep track of that somehow. So let's see, what would be the easiest way to do that? We want to say if go, right? Now we can't just say if go because that would require us to hold go high in order to count. So we could say if go or count doesn't equal 0. You guys see that? So whenever we get a positive edge of the clock, if we see that go has been asserted, and we only expect it to be asserted for 1 cycle, we would increment count by 1. Now in the subsequent cycles, once count becomes 1, then that if statement will remain true until it rolls back over to 0. You guys with me? So then you just need an assign cycle, what's it called? Cycle 7 equals, in that case you'd say count equals 4 apostrophe D7 question mark 1 colon 0. So this assignment statement would just assert cycle 7 in whatever cycle the counter had equals 7. Make sense? I don't think you'd probably, actually you don't need the parentheses if you don't. You'd need the parentheses if it was an if statement, but not an assignment statement. Any questions? Okay. Sorry? Yes?
For the ternary statement there, if you did 4 apostrophe B 1 1 1, would that be the same?
Yep, same thing. Yeah, you could use D, H, B, O. Even O would still be 7, octal. Okay. Yes?
I have a question about question number 5.
Question 5. Okay.
So question 5, this would be a non-blocking.
Yes, those are non-blocking.
So the value of A will be the previous value of B, right?
No, okay. Oh, A is an input here, right? So A is an input. So we're relying on someone telling us what A is, right? And so the way I do that is through the table, right? So I give you the value of A because otherwise you wouldn't know what A is. But each one of these statements each one of these statements is executed because they're non-blocking. Make sure I get that right. Non-blocking. Because they're non-blocking, it means that these assignments happen concurrently, right? Meaning that the order doesn't matter, right? Now, in order to help you understand that, I deliberately reversed the order of these, right? So if I had put these in the opposite order, I would be setting B delay in one line and then using B delay in the next line, right? So then you'd be confused. It's like, well, wait a minute, is this B delay the new one or the old one? Well, by putting them in the reverse order, I tried to make it even more clear. But it wouldn't matter. I could take, because I used non-blocking assignment, it doesn't, the order of these statements does not affect the behavior. Does that make sense? Because the always will activate on the rising edge of the clock, And assigning these values doesn't do anything within the context of that clock edge. After the clock edge is when the stuff takes effect, right? Does that make sense? And the only reason I mention this is it has to do with dependencies. It has to do with if you get a clock edge and you set something and then something else uses what you set as an input, what do, right? That's the question that's being answered by the non-blocking versus blocking, right? It's when I think that's a concise way to describe it. It's when you assign something according to an event, which the event is the clock edge, right? When you make a change to the state of a signal on a clock edge, but on that same clock edge, you use that signal as an input. What does the input look like? Is it the new value or the old value, right? That's the problem we're solving with these two different types of assignment statements, right? So in this case, now in this problem, it doesn't make any difference. That's, you know what I mean? Or would it? If I had used blocking, would it? Actually, that's a good question now that I think about it. If I had used blocking assignment, maybe it wouldn't. Maybe it would matter because even though I assign B delay last, it may still affect this B delay. This B delay. This B delay 1 is set, and I set it on the rising clock edge. Is this the old version of it or the new version of it? Well, you would think. Yeah, I mean, you think, well, it should be the old version no matter what because it came first. I referenced that before I said it. But it's Verilog, it's concurrent semantics, so you can't, there's no guarantee of that. Actually, now that you mention it, I'll have to test this out. I don't know for sure, but it could be the case that if I had used just blocking assignments, then this whole thing would have collapsed down into one cycle of delay, right? Because I would change B delay 1, and then this line of code would see the new version, not the old version, even though it came first in the code, right? Because I don't think the ordering of these. I'm not sure. I have to test it. I'm actually not sure. That's a good question. But I was deliberately trying to create a delay line here, and so I use these non-blocking. And with the non-blocking, the behavior is clear. This is going to be a 3-cycle delay. Meaning that, and by the way, this is very common. This is a very common thing to do. There's a lot of times when you want to delay, like if you have a pipeline and a processor and you have a result and you generate a result, but you don't need it for a few cycles, you don't need it until later in the pipeline, you just delay it. You just create this, what I call a delay line. Some people call it delay register. Also, this concept appears if you take digital signal processing, they have these notions of delay lines for digital filters as well, because you have to take samples and delay them in the digital filter, right? Sorry.
B delay 1 would be one previous value of A.
Right, so B delay 1 in cycle 0 is kind of undefined because it's like there's no cycle -1, except I have an initial statement that resolves that uncertainty, right? So the initial statement says that initially B delay 1 is going to be 0, so that's going to be a 0, right? But in the next cycle, the initial statement is no longer in effect. So in the next cycle, B delay is going to be a 0 because B delay 1 in cycle 1 is going to match what A was in cycle 0, right? The previous cycle. So B delay 1 will be a 0. In the next cycle, it'll be a 1. In the next cycle, 0 and 0. So you could think of it like if I could draw an arrow, like each row represents a clock cycle. So when I go down one row, I'm going one cycle into the future. So if I take that value of A and kind of have a diagonal arrow, it'll move it into the next cycle of B delay, right? And then that happens in stages until B. So what that means is that B in cycle 3 is going to be what A is in cycle 0, right?
That, I'm still confused, but that has nothing to do with the order of the thing, right?
No, it has nothing to do with the order. It's just saying, it's just the, this is creating basically this is creating flip-flops that are connected in series is what it's doing. Right. It's creating a shift register, but it's a multi-bit shift. Is it? No, it isn't. It's just a regular shift register. It's only each of these are 1 bit. So it's a shift register. So it's taking the bits and shifting them down one slot at a time. But the slots are named. The slots have named B delay 1, B B delay 2, and B. So it's like having a 3-bit shift register, but each bit has its own special name, right?
So if there was like a delay 3, it would be a 4-bit.
Yeah, that's right. Yeah. We could create a serial to parallel converter out of this too. Like if you shift these bits of A down into these slots, 3 cycles, then we could read them all 3 at the same time. And you know what I mean? So we could shift in 1 bit at a time, but then read out 3 bits at a time. Every 3rd cycle we could shift out, create a serial to parallel converter. Okay, great. Any other questions? Okay. Well, while we're talking about it, let me might as well do the review. Actually, I'll save these other ones for Monday. I don't want you guys to forget this stuff until next Wednesday. Okay, so starting chapter 5. This chapter is on digital building blocks. The way this book is organized is chapter 1 is the fundamentals of chapter 2 is combinational logic and Boolean algebra. Chapter 3 is the sequential logic. Once you know those two, you know enough about digital logic to be able to write in hardware description language. And once you know how to write in hardware description language, you can start building components that could be used to form complex digital systems. So where this is all going is chapter 5, we're going to talk about how to build some building blocks, arithmetic modules and memories and things of that nature. And then eventually you're going to take those modules and we're going to put them together to form a processor. So we're kind of building a processor from the bottom up, right? We know the HDL, so we have the tools to design these things. And so you start simple and you build up and you eventually can get something like big GPU or whatever you're building. Okay? So a good place to start is with the adder. I think you guys probably covered adders, at least simple adders, in 211. You remember the half adder versus the full adder? Anyone remember that? So the first question that I know I had when I was learning digital logic was like, oh, Boolean algebra, it's pretty neat. It's got ands and ors and complement. But to what end? What is this? I mean, who uses Boolean? What is this useful for? What are we going to use this? No one cares about Boolean logic in real life. What you care about is numbers, arithmetic, number crunching, right? Computations, right? Boolean algebra is kind of simple, right? So the question is, how do you take Boolean algebra and use that to build more complex operations? And so a good place to start is adder, adding 2 numbers using Boolean logic. How do you do that? It turns out it's actually it's kind of complex, especially when you think about performance and how long it takes to do an add, how many gates it takes, and that kind of stuff. So generally you think of these as you break it down into a simpler problem. If you want to add 2 n-bit numbers, you add each of the pairs of bits in A and B individually, much like you do like if you're doing long addition on paper, right? You guys with me? So the book uses this terminology of columns. You see this come up a lot. They'll talk about how one column affects another, which is a little confusing, but a column is you have to think of a column as like when you add anytime you add 2 numbers, you just line them up, you line up the digits of the 2 numbers, and you add them individually. So, 147 plus 201, add 7, 4, 3. You add the numbers individually from least significant to most significant. So when the book talks about columns, it's talking about these columns. Each column represents 1 digit of each of the inputs, the corresponding pair of digits from each of the 2 inputs, as well as their corresponding digit of the sum. Does that make sense? That's a column, right? So a full adder is a way to implement a column of a binary adder, right? So it basically adds 2 digits and produces 1 digit of output, 1 digit of sum. You guys with me? Right? Seems straightforward, right? It's basically an adder that adds 2 single digits in binary, and since a binary digit is just a 0 or 1, it's basically just adding 0 plus 0, or 0 plus 1, or 1 plus 0, or 1 plus 1. That's it. There's only 4 possibilities. The problem is you have to also worry about carries. So you have to be able to carry from one column to the next. So if you overflow one of your columns, and this, like if you add 199 plus 299, 9 plus 9 is 18. I've overflowed. That column is got to carry. So you have to carry out, right? And that's the problem here, is that you have to consider these carries. So if you're going to implement each column as one module, you're going to break it down into modules, you have to account for the carries. And in the case of a full adder, you just consider the carry in as a third input. So it's really like just creating you're adding 3 numbers, 3 bits, right? Likewise, if you're adding 3 bits, you have to have 2 output bits, because you could add 1 plus 1 plus 1 is 3, and you need 2 bits to represent 3, right? So there's a carry out, and that carry out is kind of the what would carry to the next column. So it's pretty natural then and then you can build the truth table for this. The sum bit is going to be a modulo 2 operation, meaning that your sum is going to be 1. In binary, your sum bit is going to be 1 whenever you have an odd number of input bits of the 3 inputs, right? So if you have, like, for example, 001, 010, 100, that's 1. One of the 3 inputs is 1. Or if all 3 of them are 1, you have a 1 of the sum, in the sum. You guys with me? So it's a modulo, which is also the same as doing an XOR. A 3-input XOR is a modulo 2, also known as a parity operation. You guys with me? Is there an odd number of 1 bits? Right? The carry out is going to be set whenever at least 2 of the bits are set, right? So if I've got 2 or 3 bits or 1, then my carry out is 1. Okay, so in 211 you probably covered the ripple carry adder. The most natural way to create a multi-bit adder is to take full adders and chain them together, where each adder's carry out feeds into the next adder's carry in, right? That's a ripple carry adder. The problem with that is the propagation delay. Because in order to figure out this adder, in this case, this is the most significant of the full adders in this array, depends on the carry out of its previous one, which depends on the carry out of its previous one, going all the way back to the first carry in. So the delay is going to increase as you add bits, right? So it's too slow. It's easy. It's an easy design, but it's just too slow. We want to be able to have adders that work faster. Why? Because adders are the building blocks of multipliers, right? And comparators, and dividers, right? In fact, just about everything you do in a processor does an add. Even load and store operations have to do an add, because they have to calculate the address that you're loading or storing to. Branch instructions have to use an adder so they can do a comparison. And every sort of arithmetic operation imaginable also is based on an adder, even floating point. Even when you do a floating point operation, it's doing comparisons in the exponent field, it's doing adding in the exponent field if you're doing a multiply, it's doing adding in the significant field if you're doing an add or a subtract. Everything uses an add. Everything, literally everything you do with a computer does an add at some point. So this has to be, this is going to determine the entire speed of your computer, essentially, how fast you can do an add, right? Everything's built on top of that. So, how do we make it faster? Well, there's many ways to do adders. Because they're so important, there's been a lot of attention given to making adders fast. And by the way, when I first saw this, I was like, wait a second, hold on. You said that we have a synthesizer, right? Right? The whole idea was that if I give a truth table to the synthesizer, it will generate logic for me, right? In fact, the synthesizer can generate different versions of the logic where trade-offs are made between gates and delay, right? So why do we have to worry about this? Why not just build a truth table that performs the adder and give it to the synthesizer? Problem solved. It'll generate a customized circuit that does an add, right? Make sense? Just give a adder truth table to the synthesizer and you're done. It's an adder. It'll generate the logic. Anyone see the problem with that? It's not practical to do that because the adders get too big. There's too many input combinations to build a truth table for an adder, right? You got 2 inputs of n bits. That means there's 2 raised to the 2n power rows in that truth table, right? So it's not practical to do it that way. And if you tell the synthesizer just to do an add, like I did over here with this counter, right? Over here, notice I just put an add in there and I just said, hey, do an add. Well, the synthesizer has to know how to implement that add, and so it's going to rely on this predefined ways to do adder architectures. You guys with me? So we have to know how to build. So building an adder is not something that can be done systematically. It's something that needs to be, some designer had to figure out how to do an adder, is I guess my point. Okay, so one way to do it is carry-lookahead adder. So the problem here is that we want to try to make the carry chain shorter, essentially. We don't want to have, so the problem is in terms of gate delays, by the way. So you've got a carry in, it goes into the first adder, which propagates through the first adder, becomes a carry out, then it goes into the carry into the next adder and goes through that one and becomes a carry out. Every time you go through, every time the signal has to percolate through a full adder, it has to go through, several gate delays, right? You guys with me on that? Does that make sense? So if you implement your adders as sum of products form, then, or product of sums form, that means that every time you have to go through a full adder, it's 2 gate delays. So the number of gate delays will be 2 times the number of full adders you have to propagate through. We want to be able to reduce the number of gate delays, and of course this is going to cost us. We're going to have to put more gates in, but we want to go through less gate delays. So an approach for doing that is the carry-lookahead adder, where instead of waiting for instead of waiting for signals to propagate through the previous columns to get to me, when I say previous, I mean the less significant columns, I'll just go ahead and look at all the inputs and just kind of look ahead, calculate what my carry in is going to be if I had let it come through all the other full adders. Does that make sense? Right? So generally speaking, there's this concept of generate and propagate. Every column, and again, column is referring to pairs of input bits, which in terms of like a ripple carry adder, it's referring to one of the full adders in the array of full adders. Every column that's noted by its bit, I, which for a 32-bit adder would be 0 to 31, right? Every column generates in addition to the sum and the carry out, it also generates a propagate and generate bit. A generate means that this column is going to produce a carry out regardless of what happened before it in the array. So, do I have an let me show a picture. I think it's a little easier. So if I have this 4-bit adder, I want to add A, and B. So A3, B3, A2, B2, A1, B1, A0, B0. All right, so I have these full adders. Normally, I would have these carry chain here. Carry in, carry out. Right? This is carry in 3. Right? Carry in 3 is going to depend on the output of this full adder, which depends on its carry in, which depends on the output of this full adder, which depends on its carry in, which depends on the output of this full adder, right? That's the problem. I want to be able to look ahead and pre-calculate. This guy wants to say, you know, what is my carry in as a function of these guys, not as a function of the carry ins. But an easy way to do that is to add some outputs to these adders called generate and propagate. So this is generate 2, propagate 2, generate 3, propagate 3, generate 1, propagate 1, generate 0, propagate 0. So if this generate is set to 1, it means that based on A and B alone, this guy's going to generate a carry. Doesn't matter what happened with these guys. If A and B, if A2 and B2 are both 1, this guy's going to generate a carry no matter what. Right? Make sense? I can ignore everything else. It's like saying, you know, when you do decimal, like if I'm adding two numbers, 199 plus 120x, right? I don't even care what that digit is. I know that based on those two digits alone, I'm going to have a carry into this row, right? Now it's decimal, so I don't know what the carry is going to be. But since this is binary, my carry can only be 1 or 0, right? So generate means I generate a carry. Propagate means that I'll generate a carry only if its carry in was 1. Meaning that if a carry came in, I'll pass it along. So what conditions would that be true? Well, if let's say A2 was 1 and B2 was 0. So one of my inputs was 1, the other was 0. Could go either way. I could have a carry out there or not. It depends on the carry in. You guys with me? Make sense? Okay, so that way, I can calculate carry in of 3 internally inside this guy. In fact, I can just erase these because I don't even care anymore. I can erase the carry lines, and I can calculate the carry in internally using these two guys. It's going to be generate 2, right? Or propagate 2 if I had a generate in 1, right? You guys follow that? Right? So if this guy was propagating and this guy generated, it will pass through, right? But what if I have a propagate in 2 and a propagate in 1? So let's say this one propagated and this one propagated, but I generated 1 here. Generate 1, generate 0. Right? Or let's say I propagated in 2, I propagated in 1, and I propagated in 0, and I had a top level carry in. My carry in 0 was set because that's provided by the user. You guys with me? Make sense, right? And then I could do a little manipulation here. I can say, well, that's kind of long. What if I say propagate 2, or I can distribute propagate 2 out of there, and I can say propagate 1 or, I don't know, how's that work? Propagate 2 and generate 1, or propagate 1, generate 0, or propagate 0, carry in 0. Right? Right? Or, right? Oh no, that's it. That's it, right? Yeah. And another parenthesis there. 1, 2, 1, 2. Yeah. Make sense? So this way I break the carry chain, but I still need to look at all these generate and propagates from these guys. But check that out. Look at that. I can calculate the carry in now in 2 gate delays because this is product of sums. Sum of products, right? Now I'm not including the gate delays it takes to calculate generate and propagate, but those are pretty simple, right? What is generate and propagate? Well, that's basically, generate is when A and B are both 1, right? Yeah, generate is whenever my 2 inputs are 1. That's simple, right? And propagate is when either one of them are 1. So generate is A and B, propagate is A or B. Everyone see that? That's pretty fast, right? So I don't have to wait, I don't have to propagate all the way through that. Now, in this case, it's not that much faster because it's only 4 bits. So I only had to go through like 4 gate, or well, let's say 2 gate delays. 1, 2, 3. I had to go through 6 gate delays to get my carry in on this guy with a ripple carry. With this carry look ahead, I had to go through 1 gate delay to get generate and propagate plus another 2 to get carry in. So I'm looking at 6 gate delays versus 1 versus 3. So this is the ripple carry versus carry look ahead. So I halved my time. It's pretty good. But 3 gate delays is not a big deal, really. Right? This becomes more important as we scale up. The problem is, you might be thinking, wait a second, hold on. This thing is pretty big even for 4 bits. Look at how big this thing is. Look at all these, right? Are we really going to scale this up to 32 bits? That would be really ugly. Right? Because you'd have to have this huge expression to do this, right? This would get ugly fast. So the solution is you can build these things hierarchically. You can sacrifice a little bit of delay to simplify these things quite a bit. The way they do it is that you can generate, propagate, and generates for blocks of columns, for multiple bits. You guys with me? So the way you do it is, your goal is to figure out, your goal is to create a generate and propagate that covers all of these guys, right? So in this case, generate 3:1. So before, this was like generate 2, right? Generate 3. But this says 3:1. This covers 4 bits. This is the generate that covers 4 bits, right? And you can build it from the individual generate and propagates of the columns that are inside that group of 4. You guys with me? So generate 3 down to 0 starts out by saying generate 3. Well, that's simple. If the most significant bit of my group generates, then the whole damn group generates, right? Or if I propagate 3 and I generate 2, or if I propagate 3 and I propagate 2 and then generate 1, or if I propagate 3, propagate 2, propagate 1, and propagate whatever the generate was on the previous block. Or sorry, no, that's propagate 0. That's generate 0. That's not the previous block. That's the least significant bits generate. Sorry. You guys with me? Because we're not calculating the carries here. We're only calculating the generate and propagate for the block. So we're not worried about the carries yet until we use these to construct the adder. You guys with me? I'm sorry, I didn't mean to confuse you. The propagates are even simpler. It's just if all of the propagates are set, then if all the propagates within the group are set, then the whole group's propagate is 1. You guys with me? Okay? Make sense? So now we've got a generate and propagate for each bit within a group, and then we have a generate and propagate for whole groups. Is this costing us anything? Yes, it's costing us more delay, because now we have to generate the propagate and generate for each bit. That's a delay. But then we have to send those through and generate 2 new propagate and generates for the groups. That's going to add 2 more gate delays. Right? So we're delaying a little bit more, but it's still better than a ripple carry. So the book shows this diagram. I think this is pretty nice. This is the 4-bit carry-lookahead adder block, which is the way I described it here, where each bit generates its carry in based on the generate and propagates of the other bits in that group. You guys with me? And frankly, you probably don't even need to do that. I mean, like I said, I mean, you're not really saving much from doing you're not saving much from doing carry-lookahead within each group of 4. You guys with me? I mean, you're going from 6 to 3 to 6 gate delays, whatever. It's not a big deal. So you could do ripple carry within each group, right, if you wanted. You still have to generate the P's and G's for each bit, but the way that you calculated the carry-ins internally doesn't really matter that much. But the point is that once you've got these 4-bit groups of 4, and you got the generates and propagates for this group of 4, you could use it to put these groups of 4 together, and you can calculate the carries between each group of 4 as a function of the previous propagate and generates of the previous groups. You guys with me? So in other words, this group bits 27 down to 23, for instance. 27 down to 23? Oh yeah, because that's, oh sorry. Well, it's wait a minute, is that numbered? Yeah, 31 down to 28. Yeah, 27 down to 20. Yeah, 27 down to 24. Yeah, sorry, I got that confused there. 27 down to 4 is a group of 4 bits. It's the group of 4 bits that's second to the most significant bits of the sum. You would calculate its carry in by looking at the 6 propagate and generates from the previous 6 groups of adders. You guys with me? Does that make sense? Not sure how well I'm describing this. Okay, well, we're out of time. I will continue this on Monday. Thank you.
I would have to put a request in for next week's exam.
Okay.
So I guess I'll confirm with you